So first of all, thank you very much for the thank you very much for the invitation to speak here. First, a couple of apologies. So I got a cold. So if you hear me coughing, please excuse. Also, I had to wake up the kids and do the school run this morning. So unfortunately, I missed out on the first lectures. I hope I'm not too repetitive in the review part. Um, I'll talk a little bit about higher connections, higher Chern-Simons theory. I've been working on higher connections for a while, motivated by M theory. And there are some interesting features that arise in this context, and you can already see that coming from L-infinity algebras. And I'd like to talk a little bit about this because there are some challenges in higher Chern-Simons theory that arise from this. So the materials presented is joint work together with these people over here. The people in red don't have a job yet. They are all excellent. So if you see them on the market, grab them. They're really good. Okay. So why would you be interested in higher connections from physical perspective? As I said, I've come from my motivation originally comes from M theory. So I looked at M5 branes in particular. I was interested in those. And if you look at string theories, then you know that D branes, they interact via strings that end on them. And the effective description is a kind of a theory of endpoints. And the parallel transport of these endpoints gives you gauge theory, gives you Yang-Mills theory. And a lot of study in string theory has actually been done via ordinary gauge theory and has been very successfully done via ordinary gauge theory. If you now lift this up to M theory to try to learn a little bit more about M5 branes, then you see that M5 branes interact via M2 branes. And these M2 branes, they don't end in a point, but they end in a line. So the effective description, if you mimic the analogous story of D branes, should then be a theory of self-dual strings, namely these strings that are the boundary of an M2 brane and an M5 brane. And if you look at the parallel transport of these strings, so if you have an extended parallel transport, then you get what's called a higher gauge theory. And then there's this famous theory X, so there's 2-0 theory in 6 dimensions. That's, of course, very interesting. That is also conjectures to describe multiple stacks of multiple M5 branes. And there's lots of hints that this should be a higher gauge theory. And the question is, okay, could that be a classical higher gauge theory? Could we describe that in kind of Lagrangian like we do with Yang-Mills theories? But altogether, I want to say that higher connections are really ubiquitous in string theory, in supergravity, in particular in the context of gauge supergravity. And we'll come to that back in a second. Okay, then if you're a mathematician, why would you be interested in higher connections at all? Well, these higher connections, and particularly these M2 branes ending on M5 branes, they give you higher forms of instantons and monopoles. And if you remember the development in the 80s and 90s, they were really crucial in building this very successful bridge between differential geometry and theoretical physics, in particular string theory. And if we can get higher forms of these instantons and monopoles, that should be hopefully equally interesting. So for example, we will encounter a string structure on S4, which is like a categorified monopole, categorified instanton, apologies. And altogether, we expect a very rich mathematics. So there's a Nahm transform, including a Dirac operator. And if we lift this, we may say something about categorified Dirac operator, which is a long-standing open problem in mathematics. Then there's also the topic of higher geometric quantizations. So these M2 branes end on the M5 branes, and we expect that each point of the M2 brane polarizes into a quantum 3 sphere. And to describe that accurately, we would need a higher form of geometric quantization that describes that. And of course, then there's theory X with all the dualities and all the mathematical implications that may be very attractive. But there may be lots of further reasons that I may be interested in studying higher connections. In particular here, probably higher Chern-Simons theory may be very interested. You can conjecture then that there's related to higher knot invariance. Then there's very nice description of T-duality and generalized geometries and higher versions of these that you can discuss using higher connections. And altogether, you get really, really interesting structures. For example, we defined a new homotopy algebra. And there's really interesting mathematics underlying that. And the general law is, that categorification is a little bit like deformation theory. If you want to understand a mathematical object, it's always good to study its categorification because that allows you to study and extract the essence of that mathematical object. Okay, quick outline of what I would like to talk about. So first of all, I give a quick review. What's subtle about connections in higher bundles? What do you need to do? And the story is essentially you cannot just do the naive definition for non-flat connections. You need an additional datum, and we call that an adjustment. I'll then talk a little bit about what we know about these adjusted connections, because we have a couple of interesting examples, and we have glimpses, at least, of the origin of this adjustment data. So first hints of interpretation, in some cases at least. But there's a lot that we still don't know, right? So I'll tell you a little bit what we do know, and at the very end, I'll tell you what's not known, which is probably more. And finally, then I go to a higher Chern-Simons theory and explain why what you need in that context then ultimately. Okay, so what's subtle about connections on higher bundles? Let me quickly review L-infinity algebras. You probably have seen that already in all kinds of guises and all kinds of forms, but maybe it's pleasant to hear something that you already know in different form, but at least it establishes my notation. So L-infinity algebras are generalizations of differential graded Lie algebras. And in the bracket picture, you essentially have a differential graded vector space over here. I'll always denote it by a frac L. And you have a differential, mu1, so you get an underlying differential complex. And then you have also graded totally antisymmetric multilinear products, mu I, which go from the I-fold wedge product of L in L, totally antisymmetric. And in my conventions, they will always have degree 2 minus I. And these satisfy the higher or homotopy Jacobi identities. So the Jacobi identities, but all the identities lifted up to homotopy. And explicitly, if you unfold this equation, you know that they look as follows. Mu1 is a differential. Mu1 is a derivation of mu2. And the Jacobi identity holds up to the homotopy given by mu1, mu3 plus mu3, mu1, right? This is schematic writing, but I guess you've all seen the homotopy Jacobi identities. So let's not dwell too long on this. Then a couple of examples is always helpful. We have the trivial L-infinity algebras where always the vector space are all of degree 0. Then a Lie algebra is, of course, an L-infinity algebra. It's concentrated in degree 0, so that means the only non-trivial vector space sits in degree 0 over here. And then you can build lots of other examples. For example, you can take a Lie algebra, you can take a representation of that Lie algebra on a particular vector space. And then you can bundle this up in a two-term L-infinity algebra concentrated in degree 0 and -1. So in degree 0, you just have the Lie algebra as before, and you extend it on degree -1 by the vector space, and then the higher products just act like this, and the differential is just trivial. So the above examples of L-infinity algebras are all strict L-infinity algebras. That means that they are nothing but differential graded Lie algebras. So instead, let me give you an example which is not just a differential graded Lie algebra and also concentrated in non-positive degrees. And this is kind of the archetypal example of a higher Lie algebra. You can see it as a higher form of the spin Lie algebra, which actually in a very precise sense. And I'll call this a string Lie2 algebra. And the way that this looks as, it's almost like this representation here. It has spin n sitting in degree 0. And it has an additional factor of r in degree -1. The differential is again 0, and the brackets are the natural brackets that you can write down. Namely, there's a binary bracket, which just is the Lie bracket on spin n. And then you have a ternary bracket, which is just the Lie bracket combined with the killing form. And in spin n, if n is larger equal 5, you have a canonical generator of H3 spin, and then you can choose a normalization of this in an appropriate way. But we can do this construction essentially for any quadratic Lie algebra. So there the mu3 is just given by this natural triple bracket. Okay, and now the important thing for our purposes is that L-infinity algebras that are concentrated in non-positive degrees, so in degree 0 and less, these can be seen as models for categorified Lie algebras. So, if you want to do categorified connections, higher connections, then we need higher structure groups and higher structure Lie algebras, or higher gauge groups, higher gauge Lie algebras. And a convenient way of describing those is in terms of L-infinity algebras concentrated in non-positive degrees. Okay, and then I'm sure that you have seen that L-infinity algebras come essentially with their own gauge theory, namely homotopy Mauer-Cartan theory. Remember that Mauer-Cartan theory for differential graded Lie algebra is just, we have a degree 1 element, which we can call a gauge potential. And then we have a degree 2 element, which is just a curvature of this gauge potential, and the Mauer-Cartan equation puts this to 0. Because L-infinity algebras are generalizations of DG Lie algebras, we can extend this in a very, very natural way. So we have the gauge potential, again, a degree 1 element in the L-infinity algebra. And then we define the curvature by the obvious continuation of this expression for the Mauer-Cartan equation that we have up here, right? Then you can introduce high gauge transformations that you would expect. So these are partially flat homotopies or just flat homotopies in this case on flat curvatures. And then you get also the Bianchi identities. And this makes up then the kinematic information of this homotopy Mauer-Cartan equation, with the curvature being 0 being the dynamic information if you want. If you also have a metric or cyclic structure, and I guess you've also seen this, then you also have the homotopy Mauer-Cartan action, namely the homotopy Mauer-Cartan equation, that this curvature is equal 0, becomes variational, and you just vary this homotopy Mauer-Cartan action, and you obtain the curvature equals 0 equation. And then, as you know from the BV formalism, is that any classical field theory, and the classical Lagrangian field theory, I should probably add, is a homotopy Mauer-Cartan theory for some L-infinity algebra. Okay, so but let me come immediately to high gauge theory, and already actually to higher Chern-Simons theory, by giving you this particular example here. First of all, recall that you can take a tensor product of a commutative algebra and a Lie algebra, and you will get Lie algebra. If you now lift this up to the level of homotopy algebras, not quite to homotopy algebras, but in that direction, then you get this generalization that if you have a differential graded commutative algebra and you tensor it with an L-infinity algebra, then you get an L-infinity algebra. All right, and let me directly go to a very important example, namely differential forms on a particular manifold M with values in an L-infinity algebra. So it's really just this tensor product over here. The total degree on this new L-infinity algebra will be just the sum of the individual degrees, so the sum of the form degree and the sum of the L-infinity degree. And the higher products are then given in a fairly obvious way. So the differential on the tensor product is just the differential on the first factor, where we have the de Rham differential from the de Rham complex. And then also the differential on the second factor with an appropriate sign, the appropriate causal sign inserted if you move an odd object, like the mu1 past an odd object, potentially odd object in the alpha one. Then for the higher products, we just use the higher products on the L-infinity algebra and move out all the other elements to the front. The fact that this is totally antisymmetric only works if this is graded commutative, and this is why this works with the differential graded commutative algebra. Okay, so this is the general example, and now I can specialize. So if I take a manifold with dimension 3 plus n, and I use an L-infinity algebra that's concentrated in n plus 1 degrees, non-positive degrees, so starting at 0 and going all the way to minus n, and I perform this construction, then the differential forms that I get are essentially those of n-categorified Chern-Simons theory, namely I have one-form gauge potentials, two-form gauge potentials, and so on. And you see, as I said, the form degree and the L-infinity degree always have to add up, and always add up to the total degree. And remember that our gauge potential was of total degree 1. And this is indeed now the case here, right? Yeah, maybe there should be plus 1 actually. Sorry, apologies. No, this is correct. Sorry, exactly. You want degree 1 elements, and this is indeed the case. So you have one form with values in L0, you have a two form with values in L minus 1, and so on. Finally, an Ln plus 1, an plus 1 form with values in L minus n. Okay, so let's make this even more concrete, and let's go to the tensor product, where we used string n, the string Lie2 algebra, you know, the one that I introduced up here, with spin n and r, and tensor our differential forms in this way and see what's coming up. So in string n, remember we have something in degree 0 and something in degree minus 1, and therefore we have a 1 form with values in spin n, and we have a 2 form with values in r. So this is the gauge potential that we have in this case for the homotopy Mauer-Cartan theory on that tensor product L-infinity algebra up here. And this is indeed a gauge potential for high gauge theory. We have a 2 form potential here as well. The higher products are given by the tensor product higher products, as we said before, and schematically I wrote them down like this. And then you can also write down what the homotopy Maurer-Cartan curvature forms are. So what you get is you get a two-form curvature, which looks like an ordinary two-form curvature that we know and love from Yang-Mills theory. And you get also a three-form curvature that has this funny form. So the dB form is, of course, what we know from abelian three-form curvature. That's the expected part. And then we get this additional part here. Excuse me. So if you compare to the supergravity literature, however, already from the early 80s, then you see that the curvatures they had in heterotic supergravity, which we expect to be related to these curvatures, is you get a different expression. You get the same two-form curvature, but you see you get a different three-form curvature, right? So here you see that something is not quite as we would expect, or not quite as we would want ideally. But then we can look a little bit further into what homotopy Maurer-Cartan theory gives us, and we encounter a few problems that are not as nice. So if you look at the gauge transformations, for example, for homotopy Maurer-Cartan theory, and I guess you have seen how to define them, or you know how to define them via homotopies, essentially, then you see that the commutator of two such gauge transformations in homotopy Maurer-Cartan theory does not actually close. It closes up to a gauge transformation again, up to higher terms which contain the curvature expression, right? And also, if you look at higher gauge transformations, this, by the way, is a generic feature. It's not just gauge transformations, it's also higher gauge transformations that exhibit the same feature. If you take the commutator of higher gauge transformations, it also doesn't close. It also produces terms involving the curvature. And also, high gauge transformations are not globular. What I mean by this is the following. So if you look down here and you have, for example, a gauge potential A, and you perform a gauge transformation, you get a gauge potential A tilde. Now you expect that a higher gauge transformation will map this particular gauge transformation to another gauge transformation, which also links A and A tilde. However, if you do the computation, if you see what actually the effect is you don't get the same gauge potential, you get a difference, a little delta, and this delta is again proportional to the curvature of your original theory. Right, so what this means is that the gauge transformation and the higher gauge transformation, they act exactly as you would expect if this curvature is equal to zero. However, if this curvature is not equal to zero, and this is what we ideally would like to have in the context of gauge supergravity and so on, this is not working, right? So the gauge structure that you get from homotopy Maurer-Cartan theory is unfortunately not quite correct, and the high gauge transformations are also not quite correct. And these problems, if you dig deeper, they persist. So if you look at the higher power transport for such connection, then the literature just tells you it's not per reparameterization invariant, and this is old work by Schreiber and Bias. And this is again the same problem. It's only reparameterization invariant if certain aspects of the curvature vanish. Then maybe you're interested, like myself, in the to-zero theory. So this has in particular, it's a six-dimensional theory, and there's a two-form potential with a three-form curvature, and you would like this three-form curvature to be self-dual. However, if the curvature is turned on, then you see the gauge transformations act like this. And in particular, you know, the self-duality condition is essentially not gauge covariant, so you cannot have this as an equation of motion. Now, the literature, so essentially so far until 2012 or so, if you look into papers on high gauge theory, they usually propose the following solution, that you impose fake flatness. That means, in particular, if you go back to this higher gauge theory that we had here, where you have a one-form potential and a two-form potential, that you say, well, the two-form potential is actually flat. So we have actually flatness in the two-form curvature. The problem of this fake flatness condition here, you see it solves a covariance because this term just drops out. So this is all fine. And it indeed solves a lot of problems. But what you can show is if you impose this condition, then your high gauge connections are actually locally abelian. And what this means is that if f is 0, you can essentially gauge away the one-form connection part completely. And you can show this rigorously, so that mathematicians have shown that, but you can directly see that for physicists by inspection. It's very, very easy to see that. everything becomes locally abelian. And that means if we go back to this theory here, that A is 0, so F vanishes, and what we are left with is just an ordinary abelian high gauge theory. And this is not interesting enough for what the things that we want to address, right? In particular, yeah, abelian higher gerbs, higher principal bundles have been discussed in the literature for a while, and they've been known, and this is all fine. But we really want to have some form of non-abelianity or something like this, because we would like to have meaningful interactions of our two-form potentials as well, right? And also we just know in supergravity we have certain situations where F is just not 0, so this doesn't fit. So this solution is not good enough for our purposes. Also, if you then look at higher Chern-Simons theory, if you impose that, you get problems, but we'll come back to this later. Okay, so what is the solution of this and why does this appear? Let me give you the example of two connections. So again, we go to the general situation where we have an L-infinity algebra concentrated in degrees 0 and -1. And we have a one-form and a two-form potential, right? So that's the first level of a categorified connection, this paratransport of extended strings, essentially. So for this one-form and two-form connection, of course, we have a two-form and a three-form curvature, F and H. And then we have gauge transformations, which is given by a 0 form with values in L0 and a 1 form with values in L-1. And then there's also the higher gauge transformations, the gauge transformations between gauge transformations, which are given by a 0 form with values in L-1, right? These are all at the infinitesimal level. I just use L-infinity algebra technology here. And now what you do is you take the gauge transformations for your potentials, and this is the blue expression over here. And then you realize that homotopy-Mauer-Cartan theory is, of course, a theory of flat connections. So anything that involves the curvature is not seen. And what you can do now is simply you can say, well, I can deform the gauge transformation for my two-form potential by adding an additional term that contains the two-form curvature, right? In the flat case in homotopy-Mauer-Cartan theory, I will not see that because F is 0, right? But in the general case, if I want to lift flatness, if I want to go away from flatness, I can, of course, introduce this additional term, right? And once you do this, you see that you can make everything work if this additional term, this additional algebraic datum, which we called an adjustment, satisfies two conditions. And these two conditions are the following. So first of all, if I act on something mu1, that's mu1 of something, I want to get this expression. I want to get the action of x and y. And second, the action of a degree 0 element on this kappa should be given by this expression, right? So if my kappa satisfies these equations, then everything is okay, and I can define the higher gauge transformations in a consistent manner, and things work out as expected. The important thing is to see that because if the mu2 is non-zero, of course, kappa cannot be chosen to be 0, right? And this is exactly the problem. Also, if mu3 is not equal to 0, kappa cannot be chosen to be 0. So there are a couple of extreme cases. There's a couple of cases where this mu2 is indeed 0 and mu1 is 0. That was the case for the string Lie-2 algebra that I presented before. But in this case, mu3 is not 0. So in all of these cases, you see really that the conditions for having consistent gauge structure usually tell you that kappa cannot be 0. There's a few exceptions, but these are very special and they're usually not that particularly interesting. The other thing that I should mention is, of course, because gauge transformations are partially flat homotopies, if you change the gauge transformation, you also need to change the definition of your curvatures. And we have here, here you see what happens. The two-form curvature stays the same. Sorry, this should be mu1. And the three-form curvature now gets modified also by this map kappa, and it gets this additional term. Okay, so now we have the infinitesimal gauge transformations working out nicely, and the higher gauge transformations, everything acting as expected by deforming that. And what's now nice, and maybe you're interested in this, what you can integrate this all up to finite gauge transformations and finite high gauge transformations. So you get a finite gauge groupoid. So the BRST algebroid integrates nicely to a higher BRST groupoid, and then you can stackify the whole thing. That means you can define corresponding higher principal bundles with connections, and that all works fine. So at the end of the day, once you deform the gauge transformations of the higher form connections, with suitable adjustment data, with suitable deformation information, then everything will become consistent and you get higher bundles with adjusted connections. So mathematically, everything is fine now. So the general story is then as follows. Higher principal bundles can be defined straightforwardly at at the level, be it in terms of check homology, so transition function also. That's usually not a problem. I mean, you can make your life arbitrarily complicated by using arbitrarily abstract spaces, but if you want ordinary higher principal bundles over ordinary manifolds, it's not a problem. You can define them. Flat connections on higher principal bundles can also be defined straightforwardly. There's a very nice mechanism that I could tell you about more if you're interested in. And so these parts are not difficult. What is difficult is go from the flat connections to the non-flat connections. And for those, you then define this adjustment data. That means you deform the gauge transformations on your higher form fields. And usually then you get algebraic conditions on these, as I showed you for these once categorified connections before. Yeah, and this induces deformations of also of the curvature and the Bianchi identities, and then you can define the full bundle transition functions for your gauge potential. And the important thing is that the resulting connections that you obtain in this way are really the ones that people encountered in supergravity. So if you look at heterotic supergravity and in particular also in gauge supergravity, these connections can be obtained exactly in this manner, right? I mean, usually these are constructed a little bit by hand, but if you would like to know the higher principal bundles that are underlying it and how this really is glued together appropriately, then you go through this machinery and you get exactly the connections that appear in supergravity. As a little side note, this is not only relevant for high gauge theory, but you have a similar situation if you looked at a gauged matter theory, where you essentially have a Lie groupoid of gauge structure, right? So you have your matter fields and you have your gauge group acting on the space on which the matter field takes values. That gives you an action Lie groupoid. You can bundle this all up into an action groupoid. But more general, you can define for any Lie groupoid, you can define gauge theories. And in this case, you also have this level that you have kind of two levels of curvature forms, namely you have the covariant derivatives on your matter field, you have also the curvatures themselves, and therefore you also need to, or you also have the freedom at least to impose an adjustment. Here the case is for gauge matter theory, you can put the adjustment to 0, and this is why you're not aware of that. In the standard model of elementary particles, for example, you don't see this. But in principle, there may be room for such adjustment. And the literature on this, I mean, the first form of these adjusted connections, in a sense, were hidden in the supergravity literature, in heterotic supergravity back in the 80s. And then special cases were developed by Saty, Schreiber, and Stashev, 2008, 2009. And then we did the general theory. I mean, they were motivated a little bit differently, I would say, by matching the Green-Schwarz anomaly cancellation condition as a Bianchi identity. But actually, if you want to consistently have a higher gauge theory with a higher gauge transformations working correctly, then you should do this adjustment procedure anyway. Okay, so now having talked a little bit about the abstract context, let me tell you a little bit what we know about adjusted connections, and in particular give you some examples. So first, let me also venture a little bit into the world of higher principal bundles, and for that I would like to integrate the two-term L-infinity algebras that we used so far as higher gauge structure. If you use a strict two-term L-infinity algebra, then you can integrate this into a cross module of Lie algebras, right? I don't want to go into the details of what these cross modules are. They are good examples of higher groups. What they look like is essentially you have two Lie groups or two groups, yeah. If you have G, group G and group H, together with a group homomorphism T. And the interesting thing is that these higher Lie groups are actually classified by the kernel of this map T and this co-kernel of T, right? So if you use weak equivalences, so the integrated forms of quasi-isomorphisms of L-infinity algebras, then what is preserved under those is really the kernel and the co-kernel of these. And now if we introduce these adjustment maps, so we had them before for two-term L-infinity algebras, but now we would like to lift them up actually to the groups to have the finite gauge transformations, then the expectation would, of course, that the adjustment on the complement of these things that are invariant should be kind of canonical, right? They should be kind of there anyway. They shouldn't contain any particular information because under these weak equivalences, they can be added or removed to a certain degree anyway. And there we have now this following proposition. So if you look at that such a cross module of Lie groups, of course, if you differentiate it, you get a higher Lie algebra, a cross module of Lie algebras with Lie algebra H and G, and that's exactly the strict two-term L infinity algebra that I integrated. So if you have here this cross module of Lie algebras, or this strict two-term L infinity algebra, and you have a map S which splits this in this manner, so that TST is the same as T. So if I go down back with S and go down back with T, that's the same as T. Then this expression here gives an adjustment. Well, it satisfies the adjustment relations up to the kernel of T, right? So this thing that we have over here is an adjustment on the Lie groups up to kernel of T, and therefore, yeah, it gives essentially this canonical part in a sense, right? Of course, you need this map S from T to H, so you need the splitting, but otherwise you have this canonical part. Okay, and this is enough now to give you an interesting example. Namely, what I can do is I can see an ordinary principal bundle as a principal 2 bundle. Now, that may seem a little bit cumbersome. I mean, I have already the description of ordinary principal bundles, but it's a nice starting point to test if what we're doing actually makes sense and everything is mathematically consistent. So what you can show is that a Lie group G is weakly equivalent to a cross module of G, where we take the based path space of the group G, and group multiplication is just pointwise multiplication, and the based loop space of G, right? So these paths are just parameterized paths that start at the identity in G and go to some point, and these loops are parameterized loops in G that start at the identity and go back to the identity, right? And I told you before that the invariants of such a Lie cross module are the kernel of T and the co-kernel of T. So let's see what these are here. Well, the kernel of T, this is injective, so the kernel of T is just the trivial group, right? And the co-kernel of T here, well, if you have two paths that end at the same point, they differ by a loop. Oh, sorry. So if you have two paths, then they can differ by a loop up to an element in G. So the co-kernel here is indeed the Lie group G. So you see the invariance of this is just the kernel is trivial, the co-kernel is G itself. Now let's consider the Lie algebra of G, and then we have the following back and forward maps. So I can first do the boundary evaluation going on, which takes the path in a Lie algebra and just evaluates the endpoint. So I take the path and it just gives me the endpoint of this particular path. And then there's also this other map that embeds a Lie algebra element or turns a Lie algebra element into a path. And the way that you do that is you just multiply it with the path parameter. You say your path goes from 0 to 1. And then, this starts at 0 and it ends at the Lie algebra element. It's just a line in your path space, right? So you can have this. And using these maps, I can define indeed the section of T, this map here that I was looking for, this map from G to H. And the way that this works is I map a path to loop by taking the path and summing to it the path that is obtained by taking the boundary and then having a straight line from the origin to that boundary, to that endpoint of that path, right? So if you combine this, you see that the endpoint of this is just the endpoint of P, and the endpoint here is, of course, the endpoint of P. So they meet at an endpoint, and therefore you get ultimately a loop if you look at this. If you evaluate this path at 0 and 1, you get the same point at 0. Therefore, this object here, which I wrote down with this particular S, is actually an adjustment and thus a higher connection. And now you can go through the whole procedure. We have the adjustment. That means you can now go through this procedure here. You write down your gauge transformations, you write down your adjustment. Now this is already the integrated adjustment. This is already the finite one. You stackify, you define higher principal bundles, and you have then higher principal bundles with this structure groups and connections on those. And you can write this down really explicitly. And then you can work a little bit further. I mean, what you want, of course, is that higher principal bundles, because we just recoded the Lie group G into a complicated way. So ideally, we want that the information contained in this higher bundle is the same as that in an ordinary principal G bundle. And what you can then show is that the different cohomologies for ordinary and higher bundle, for ordinary bundle with gauge group G and higher bundle with a gauge 2 group, this crossed module G, they're isomorphic if this S, sorry, apologies here, I messed up. This S of F, this map S of F is indeed zero, and this is what we call adjusted fake flat, right? So we are now in the situation where indeed our adjusted connections match the expectations, and we get equivalence if we impose this additional adjusted fake flat form. Okay, but this was just an ordinary principal bundle recoded as a higher principal bundle. So now the interesting thing is, of course, do we have genuine higher bundles that are interesting? And yes, there are obvious candidates because we have really nice candidates in ordinary gauge theory. For example, we have the Dirac monopole, spin 3, which is total space of spin 3. And if we regard spin 3 as the total space of a spin 2 bundle over S2, you get the usual Hopf vibration and therefore the Dirac monopole. More interesting for our purpose is actually the doubled instanton. So you probably recall that the ordinary instanton is just a quaternionic Hopf vibration. So S7 as a total space as 3 fibers, which is the same as SU2 over S4. What we do here is we double SU2 to SU2 cross SU2, and that is the same as spin 4. So we take spin 5, sorry, as a total space of a spin 4 bundle over S4, right? And now I was traveling along over 10 years ago to Australia and talked to David Roberts about this and wanted interesting examples of higher bundles, and he was working on that for quite a while. And then he told me, well, I mean, why don't you just lift spin up to string n? So how about we just look at, in particular this one, how about we look at string 5 as the total space of a higher string 4 bundle over S4, right? And he worked this out topologically, and it's indeed the case that you can show string 5. If you divide out string 4 as a higher group, that what's left is indeed S4. And then we took this and ran essentially with it and applied our adjusted connections to it to really write down all the connections. And now the interesting thing is that for string n to get a nice model, what you can do is you can do exactly what we had up here. So you replace spin n by the based paths and the based loops, okay? And that's what's happening here. So we have the based path and the based loops. And over that loop group, we have a canonical circle bundle. And so you will centrally extend the loop group to the total space of this canonical circle bundle, which also has a group structure. And it turns out that this is a nice 2-group, and that 2-group can be identified with string n. So it's a 2-group model for string n in a particular way. So you get something very explicit. You have this 2-group, which is just a cross module of groups. It's a harmless mathematical structure. And you use this as a total space of a higher bundle, and if that has string 4 as its structure group, right? So what you can do is you can write down explicitly the adjustment of this one. Remember, I already gave you the adjustment of this particular 2-group, and lifting this up is then not too difficult. It has an interesting component, but you can write down exactly what this is. You go through the usual procedure. You define your BRST group point, you stackify, you get the explicit co-cycle data, and you can really write down everything explicitly as you would like it to be as a physicist, and you can really impose then differential equations on this data. So I would say this is the first, well, interesting in a certain way example of an explicit connection on non-abelian principal 2 bundle, if you want. And indeed, it's like a higher version of a doubled instantons. And this is also a natural string structure on S4. It's a higher version of a spin structure, right? So we do have these explicit examples going around, and everything is reasonably nice there, essentially. Another example that you can use, and let me check my time. Maybe I just go quickly through this. So, everybody here, of course, knows T-duality within string theory. And a string background that you want to T-dualize is usually in a reasonable simple situation. It's a torus vibration. So you have a torus principal bundle with a toroidal structure group. And then you have an abelian gerb on top of that. And the interesting observation now by Nicholas Waldorf is that you can combine these into a principal 2 bundle, and then a topological T-duality is just a span of principal 2 bundles, of these higher principal bundles. But if you really want to describe geometric T-duality, including the Capron-Monby field and so on, of course, you need to endow this all with connections. And then the observation is just, I mean, we did this also with the adjusted connections. So the structure group that you have up here, it comes with a very natural adjustment. And you can use that to define T-duality also to do this differential refinement of topological T-duality. So you can also see the Raman field and the connections on the torus bundle, so that you get your Kaluza-Klein metric and everything. The interesting thing here is, and this is why I mentioned this, is that the structure group that they wrote down for these principal bundles actually does not admit an adjustment. So there are higher structure groups for which you cannot do this procedure that I told you. However, the structures are all sufficient to derive the desired T-duality relation, so this is not a problem for this construction. But it's an interesting feature that certain higher groups, and correspondingly also certain higher Lie algebras, they do not admit an adjustment. Okay, and then you can do more, of course. So you can model 3 groups with 2 cross modules of Lie groups, and we derive the adjustment data for that, and the relations was a little bit of brute force computation. So this gets a little bit involved as usual if you go higher and higher in category theory. And you can write down the full differential co-cycles. And what we're doing at the moment, we want to lift this up, this T-duality picture from the past picture to U-duality, and we're almost done with that, and we hope that we get something interesting, at least not complete U-duality, of course, but at least some interesting form of lifted T-duality out very soon. As I said, you can also do this for Lie groupoids, and yes, so you can also do that locally infinitesimally, and this is the older work that we had back in 2019. Okay, but instead, let me come now to an interpretation of this adjustment, or at least a partial interpretation that we have so far. I mean, where does this datum come from, this additional algebraic datum? What does it mean? And for that, let me go back to the homotopy algebraic level, not to the finite level, so just to the infinitesimal level, because here there's something interesting that one can do. So remember, when we define higher Lie algebras at categorified Lie algebras, in terms of these L-infinity algebras that are concentrated in a non-positive degree, what you essentially do is that you lift the antisymmetry in the Lie algebra up to a natural transformation in the categorification procedure. But you usually, you leave the Jacobi identity, apologies, but you usually keep the antisymmetry, right? Your higher products in L-infinity algebra are totally antisymmetric, so you don't touch the symmetry property. However, if in the most general categorification of a Lie algebra, of course, what you want to do is you want to lift both the Jacobi identity and the antisymmetry to hold only up to a natural transformation, or then up to higher homotopies. And you can do that for the antisymmetry alone, and then you get what had been called in the literature hemistrict Lie algebras. So the L-infinity algebras were called semi-strict, and these, if you lift antisymmetry, but you keep the Jacobi identity, which then becomes a Leibniz relation essentially, you call these hemistrict. And then the observation is just that in string n, the adjustment is nothing but the alternator in the hemistrict version. Okay, and then you can make this a little bit larger story, so you can define such hemistrict versions of Lie algebras as H-Lie2 algebras. And these are just differential graded Leibniz algebras endowed with an alternator. So the alternator, it encodes the failure of this Leibniz bracket to be antisymmetric up to homotopy. And actually, you can show that for any Leibniz algebra, you can define such an alternator. So that's not too complicated. But then you can go also higher and higher, and you can make this differential graded in particular. So that's a direct generalization of Reutenberg's hemistrict two-term L-infinity algebras, and you can write down nice homotopy algebras for these. And once you have the nice homotopy algebras for these, the homotopy algebras, of course, they contain both alternators and higher Lie brackets, so they contain in particular L-infinity algebras. And what you can show them is that any H-Lie2 algebras, so any such differential graded Leibniz algebra with an alternator, can be antisymmetrized to a quasi-isomorphic L-infinity algebra. So in this higher homotopy algebras, there's always this antisymmetrization theorem that you can perform to get rid of the alternator. Okay, so why would you be interested in the alternative? I just told you can get rid of it and go to quasi-isomorphic L-infinity algebra. Well, because of the following construction. So recall that, of course, differential graded Lie algebras are special forms of L-infinity algebras. But there is a second form of constructing L-infinity algebras from derived from differential graded Lie algebras. So you don't just take the differential graded Lie algebras, but you shift and truncate it, right? So if you shift and truncate the underlying complex of an L-infinity algebra, you can define derived brackets such that you get an L-infinity algebra on the shift truncated complex. The shift truncated complex is always concentrated in non-positive degrees, so it's essentially a higher form of Lie algebra, and this is why I'm interested in that. And that's an old result by going back to Fiorenza in 2006, and then Getzler made it explicit in 2009. Yeah, and this is essentially this theorem that you can go from differential graded Lie algebras to L-infinity algebras. And now our observation is simply, well, you can refine this a little bit. Namely, what you can do is you can first shift and truncate, and if you do that, you map your differential graded Lie algebra to an H-Lie2 algebra. And then you can antisymmetrize, by this proposition that I had here, any H-Lie2 algebra can be antisymmetrized to an L-infinity algebra, and then you get your L-infinity algebra, right? So you can refine this a little bit. And yeah, so the brackets that you have here are just derived brackets, and the alternator is, because of the shift truncation, is actually just the ordinary Lie algebra that you had before. But let me suppress a little bit the details and just give you the higher picture. And yeah, actually, you may know this construction from generalized geometry because, and let me go quickly through that. The Courant algebroid, can be seen as a symplectic Lie2 algebroid. This is what Reutenberg told us back in 2002. And from the differential graded commutative algebra that we have on the algebra of functions here, together with a symplectic form, you get a differential graded Poisson algebra. Well, it's a gas number. It's a shifted Poisson algebra. It's shifted in degree. The Poisson bracket is not of degree 0. And then you can apply this construction that we had up here. And you get the Dorfman bracket as part of the H-Lie2 bracket. And the Courant bracket is the antisymmetrized L-infinity algebra bracket, right? So similarly, you can get double and exceptional field theory, but this is an example that you may know from generalized geometry in this case. But for our purposes, what's interesting is the following. So if you have a gauge L-infinity algebra, that is obtained by this procedure. So you have an L-infinity algebra, you shift truncate, and you antisymmetrize to get the L-infinity algebra. Then you get a natural adjustment structure, and the adjustment is essentially just given by the alternator, right? So by refining this theorem, we get a natural form of an alternator, and we can say that in this context, at least, the adjustment is nothing but an alternator in an H-Lie algebra. And you can write down a couple of examples. In particular, the string Lie2 algebra that I showed before can be encoded in this way. It can originate from differential graded Lie algebra, and the alternator is then the adjustment as expected. But much more larger, there's this gauged supergravity theories, and they have a tensor hierarchy, so-called tensor hierarchy of connections. And this is always constructed from a differential graded Lie algebra. And if you apply this procedure, you get adjusted high connections, and these are precisely the connections that people in supergravity constructed by hand, essentially. Yeah. And as a quick example, just to give you an impression of what these things look like. So this would be 5D maximally supersymmetric tensor hierarchy. So you have here your differential graded Lie algebra. So you have a E66, a particular a real form of the Lie algebra of E6, and then you have all these representations, and this is all packaged together in this differential graded Lie algebra. You shift truncate, and then you get this H-Lie2 algebra. You see you move every degree up by 1, so E0 is the same as V minus 1, right? You get this movement of the degrees. And then you define the corresponding brackets, the H-Lie bracket, so the ordinary H-Lie bracket, as a derived bracket, and the alternator by the ordinary Lie bracket. And then you can go through this whole adjustment procedure, and it's a straightforward thing, and then you get the adjusted curvatures. So the blue thing is the flat curvatures that you would expect from homotopy Maurer-Cartan theory. The red terms are the additional terms coming from the adjustment constructed as I explained before. Again, the adjustments are given by the alternators of this H-Lie2 algebra. And now, why is that interesting? Well, before these connections are constructed by hand, now they're completely constructed completely systematically, right? The only thing I need you to give me is this differential graded Lie algebra, and I write down immediately the curvatures for you. There's no further construction and checking of any properties or so, right? So you can just do that in a straightforward way. So in these cases, we actually know what the adjustments are. Okay, and then further interesting facts on adjustments before I come to higher Chern-Simons theory is, well, so some higher groups do not admit an adjustment. As I said before, that the one example was in this T-duality case. But, and that's interesting, they can be replaced with other higher groups that have homotopy equivalent classifying space. That means that principal bundles that have these high groups that don't admit adjustment as a structure group can be replaced by principal bundles with other structure groups, and they then do that. And the question is, well, is that a general feature? That's not completely clear. And then recently there was this paper by Ludewig and Waldorf, which did a little bit of classification of a special class of adjustments, namely for the special class of crossed modules. So it's all strict L-infinity algebras if you consider it at the infinitesimal level. But there are theorems on the existence of infinitesimal adjustments, and then also theorems on the classification of adjustment in these special cases, right? So there's a little bit known, but still a lot is open. Okay, but I also have higher Chern-Simons theory in the title, so I should finally come to that. Let's return to higher Chern-Simons theory and remember that what this is essentially is homotopy Mauer-Cartan theory for the tensor L-infinity algebra, which is a tensor product of the differential created of the differential forms on a manifold tensored by L-infinity algebra that's concentrated, should be concentrated in non-positive degrees, so that this is like the higher gauge algebra that you consider. If this was a Lie-2 algebra, so two-term L-infinity algebra concentrated in two terms, like we saw so many times already in this talk, then you can write down something like 4D Chern-Simons theory, and just looks like this. So you have one form potential A, you have a two-form potential B, and the expression explicitly looks like this. So classically, everything is fine. The solutions of this are all flat. If you assume that there's no boundary terms, you can partially integrate and derive the equations of motion, and they're just the usual flatness expression. But you may actually be interested also in non-flat connections in this context. First of all, you may want to vary this action in the more general case, right? And for that, you don't want to have any constraints on your A or your B. And also you may want to write down a quantum theory, and you may want to have a path integral that sums over all the connections, not just the flat connections, right? But if you want to do that and you want to do that consistently, you should have really a higher principal bundle with consistent higher gauge transformations underlying it. And then now, as we saw before, there are now two solutions in which you can do that. Either you impose fake flatness from the outset, so either you demand this F that creates all the problems with the high gauge transformations, you say that this is zero, and you regard this as kinematical, but then you have the problem that the variational principle does not yield total H flatness, right? So I mean, if you impose then an additional connection on your gauge potential 1 form, or your 2 form on your gauge connections altogether, and you don't have the general variation anymore, right? So you have only certain classes, and you then don't get total edge flatness, which is a little bit disappointing. Or you can follow what I explained before. You can regard this as a dynamical constraint, and therefore work with adjusted connections to have a high gauge structure. Okay, and this is what we thought then when we looked at high Chern-Simons theory. Well, the thing that you should actually be doing is you should just actually work with adjusted connections, and everything will be fine. Okay, but then you look a little bit for adjustments, and you try to find some interesting adjustments that are compatible with your cyclic structure. And then the following happens. So remember first that a cyclic structure is essentially like an invariant metric on your L-infinity algebra. So here I write them always with angular brackets, and what the cyclicity means is that you can cyclically permute the arguments in this total bracket, right? And then you get an additional sign here, as usual for L-infinity algebras, but you have this structure. Then remember that each L-infinity algebra has a quasi-isomorphic minimal model where the differential is zero. Essentially, when you have an L-infinity algebra, you remember that you have an underlying differential complex, and you can look at the cohomology of this complex, and you can define a quasi-isomorphic L-infinity algebra structure on that complex, for example, by homological perturbation lemma. But yeah, you have the minimal model theorem that guarantees that you have always quasi-isomorphic such minimal models. If you have a minimal model on your gauge algebra, right, remember this was supposed to be here our gauge L-infinity algebra, then this actually induces a quasi-isomorphism at the homotopy Mauer-Cartan level, right? So if you have a quasi-isomorphism here from L0, from the minimal model to the gauge L-infinity algebra, you also have then the quasi-isomorphism for the total homotopy Mauer-Cartan L-infinity algebra, for the tensor product L-infinity algebra. But such a quasi-isomorphism is, of course, equivalent to semi-classical equivalence. So that means that the theories would have the same tree-level S matrices if you go in quantum field theory. But yeah, you can show, of course, that this is the same. And therefore, for simplicity, we can look for adjusted minimal gauge L-infinity algebras, right? So minimal here meaning that the differential is equal to 0. And then something interesting happens, and I'll talk about give you the example of the two-term L-infinity algebra because it's easy to follow. So you have here the two-term L-infinity algebra concentrated in degree 0 and -1. And then we have the cyclicity condition. And I pulled out for you again here the adjustment condition for such a two-term L-infinity algebra. So now we notice that the first adjustment condition, because we are in the minimal situation, mu1 is equal to 0. And therefore, this L-infinity bracket, this product, this higher product has to be 0. So this product is trivial, okay? Now, the cyclicity property allows me to throw over this mu2 onto the other side, but there it will become a mu2 from L0 to L0 to L0. So this product also needs to be trivial because, you know, the cyclic structure is non-degenerate, and therefore triviality of this one follows. But if this higher product is trivial, I can go back to the second adjustment condition, and you see that this term will vanish, and these other terms here, they always contain a mu2. They will all vanish, and then I'm left with 0 equals mu3 of x1, x2, x3 in the adjustment condition. So this one is also trivial, right? So by demanding simultaneously that I have cyclicity and I have an adjustment on my two-term L-infinity algebra, the two-term L-infinity algebra turned out to be abelian, right? So there's nothing there. All the higher products actually vanish. And unfortunately, you can show that this is a general feature. There's no minimal L-infinity algebra which is cyclic, non-abelian adjusted. So if you have a minimal L-infinity algebra that's cyclic and adjusted, automatically all the higher products have to vanish. And this is, of course, a problem for us because that means effectively that we cannot use this adjustment structure on these higher Chern-Simons theory, right? These adjusted connections are just not good enough. And there's an open question of what to do, essentially, right? So what do we conclude? So altogether, you know, John Baez told us that category theory is a subject where you can leave the definition as exercise, meaning, well, you know, you have a mathematical structure, you just categorify it, you turn essentially the wheel of categorification, and you get out what you want. But sometimes, actually, you get surprising new phenomena, like these adjustments that we saw. So you cannot just categorify it in a straightforward way. You need to introduce additional mathematical structures which were invisible at the level of ordinary connections. So here something new happens. Then another important story to take home probably is that contrary to some string theory inspired myths, higher non-abelian connections can be consistently defined, right? So particularly in the context of the 2-0 theory, there's lots of rumors around in the string theory community that you couldn't define a higher dimension non-abelian parallel transport, and all of that would be problematic, and these high connections are not consistently defined. This is actually not true. You can write these down, and these are exactly the higher principal bundles with connections that you get in gauge supergravity and heterotic supergravity. So they are the ones that find already applications in string theory. So this is all fine, and this all works. We do have already quite a few interesting examples, I would say. As I said, heterotic and gauge supergravities work out. You get these string structures, so mathematically higher versions of spin structures, and we can describe T-duality spans and certain forms of U-duality spans in terms of spans of higher principal bundles with connections. I just gave you a couple of glimpses in the theory of adjustments, which is very, very much incomplete yet, but I hope I could show you that there's interesting mathematics underlying that. So we got these HL2 algebras, new homotopy algebras, and alternators were actually the origins of these adjustments. However, the big open thing is, of course, higher Chern-Simons theory. So Chern-Simons theory is much more subtle. I would say that fake flat high connections are not good. The last argument that I gave you showed that adjusted higher connections are also problematic. They're also no good. And my conjecture would be that one just needs to use different forms of higher connections. So more general higher connections may be ultimately the way forward. So we saw that at ordinary gauge theory level, we have Chern-Simons theory and Yang-Mills theory using the same principal bundles, using the same connections. At the higher level, we already saw that we need to do something additional to get the higher connections of gauge supergravity. And I believe that for higher Chern-Simons theory, you need to generalize the connections in a slightly different manner. in a way such they allow for the definition of higher Chern-Simons theory. There's interesting work, for example, by Hank Chen, and I think that he has a notion of higher connections for higher Chern-Simons theory that looks very suitable to me. But this is a generalization of the connections that we have here. So these are not the connections that we expect in heterotic or gauged supergravity. They're slightly different, but they may actually be ultimately the way forward. Yes, but thank you very much for your attention. This is all that I wanted to say.
Okay, thank you very much.